Often, when we're studying a group of objects and we just want to know how those objects interact with each other, we define them to be part of an isolated system. In an isolated system, it's also called a closed system. In an isolated system, neither energy nor matter may enter or exit the system. If we study the last example, the bouncing ball, as an isolated system, we might say that our system includes a ball. It includes the Earth because the Earth is providing the gravitational field that makes the ball fall, and then our isolated system would also include the floor. We can leave the air, for example, out of the isolated system, and that way we don't have to consider energy that's lost to friction with the air, also known as drag. So we set specific components to study. This is a simplified hypothetical situation. This is not a representation of reality because, or a perfect representation of reality, because isolated systems rarely exist. Okay, there can always be the potential for matter or energy entering and exiting a system. So this is a helpful way to study interactions. It is not always 100% realistic. Now, an isolated system is a form of what we call a model. A model, or a scientific model, is something that's used to help simulate systems and interactions, or it's used, I usually say it is used to explain a phenomenon or make predictions about that phenomenon. Every model focuses on a few specific components of a system, so every model is inherently inaccurate. It doesn't include every possibility that could ever happen in the universe. And so models are defined by the person creating them. And so they do have certain limitations. Every model has limitations. So here's an example. If a student in a biology class makes a human heart model by putting a pump or by making a pump inside a jar using a balloon and two straws, then that that could show that could show how the heart pumps. It's not a perfect representation of the heart. It The human heart has four chambers. The balloon has only one, but it can still be used to show how the heart pumps blood through the body. So this is what we consider a model. Models are not. I think sometimes there's a misconception that a model is always something you build. Models are not necessarily something you like, something physical that you can touch, that you build. They can be mathematical models, they can be drawings. They are some kind of representation that explains a phenomenon or makes predictions about the phenomenon. When we use simulations, those are also models. Here we see a model of energy conversion. This is one in which an object starts at a certain height. We can see that it has this square represents a ball. I don't know why it's a square if it represents a ball, but it represents a ball dropped in a frictionless vacuum chamber. A vacuum chamber is a container in which all of the air has been pumped out, or virtually almost all of the air has been pumped out. So we don't consider air as a factor here. Remember, when there's no air resistance, everything accelerates toward the Earth at 9.8 meters per second squared. So here we have this ball. It starts out with a certain amount of potential energy. It has, and then it's released. It accelerates toward the bottom of the chamber at 9.8 meters per second squared. And what happens halfway through that fall, or partway through that fall, or you can see as it falls, that potential energy gradually changes to kinetic energy. And then right before it hits the ground, it has almost all kinetic energy. So what is the decrease in potential energy equal to? We can say that the decrease in potential energy is equal to the increase in kinetic energy. You see in this pie chart, the total amount of energy stays the same, or the total amount of mechanical energy stays the same, but it changes in form from potential energy to kinetic energy. Right before it hits the bottom of the chamber, it has virtually all kinetic energy. When it hits the ground, when it hits the bottom, all of that potential energy will have converted to kinetic energy. And if it's a bouncing ball, then when it compresses and changes shape, some of that kinetic energy will be converted into thermal energy, right? and elastic potential energy. Okay, so how can we represent this by an equation? Well, if the decrease in potential energy equals the increase in kinetic energy, then we can write this equation. The change in potential energy equals negative the change in kinetic energy. Or it could go the other way around, right? Kinetic, multiply both of the sides by -1. You can say the increase in kinetic energy equals the decrease in potential energy. In this image, the potential energy changed into kinetic energy because energy cannot be created or destroyed. Make sure you write this in your notes. This is a big, important law of science, is the law of conservation of energy. Energy cannot be created or destroyed. It can be transferred from one place to another, or it can be transformed from one type of energy to another. So it can change its form. It can move between places, objects, fields, or systems. It cannot be created or destroyed. It's just transformed and transferred. Make sure that you understand that. That is the big idea of this entire set of notes. So let's look at an example of an apple being dropped by this young lady. Energy is measured in joules, Joules. An apple that's held 1 meter from the ground has about 1 joule of potential energy. If it falls, the potential energy is gradually converted from potential energy to kinetic energy as it falls. Right before it hits the ground, that 1 joule of potential energy will have converted to about 1 joule of kinetic energy. Notice an apple doesn't bounce very high, so that means that mechanical energy is a combination of potential and kinetic energy. That mechanical energy will convert almost entirely into sound energy and internal energy. And so the apple does not bounce very high. Oops.